Hello! We've introduced a special type of systems of linear differential equations of order 1, and we developed some theory about it. And the main outcome of the theory is that if you want to solve such a system, then we need to know how to find a particular solution, and we need to know how to solve completely a homogeneous system, which is exactly the topic for this lecture. So our system looks like this, it's homogeneous. And we also had an example in this previous lecture, which actually was not homogeneous. There were some extra parts. But then we learned that after we solved it, a certain specific part of our solution, namely this one, actually solves the associated homogeneous system. So after all, we did have a homogeneous example. And that's the kind of solution that the user would prefer. By the way, we found it using the forbidden elimination. And from the point of view of theory, it's actually better to lump these two functions into a vector function. And then we developed a, let's say, specific type of writing down the answer, which is very inspirational for us, and we will get to it very soon. So this is where we started last time, and now we will continue. And we will continue with structural theorem, and you probably expect that. Here we have a theorem which says when we are looking for all solutions of such a homogeneous system, we can find it as a linear space with a specific dimension. Dimension is given by the dimension of the system, which is nice. So we are in fact looking for a basis. In this case, the basis has a form of two vector functions. So you can notice we have a 2x2 system. So the space of solutions is two-dimensional, and therefore the basis has two elements. One element, second element. But each element is a vector. So we in fact have like 4 functions in the basis, but they are gathered into vectors. It's good to understand these things. Anyway, as usual in the field of differential equations, we like to give grand names to things. So here is our first slide for today. When we find the basis, we call it a fundamental system. We did it before, we did it again. So we have a basis y1 through yn. Now these are vector functions. So as I talked, there is actually n square functions hiding within the structure. But it's okay, we don't care at this moment. We just call them a fundamental system. But then we do start caring. Because when we have those vectors like that, we can use them as columns in a matrix. And that's an interesting object. We call it fundamental matrix. Let's have a look at it here. Our fundamental matrix is, in the first column, I put e to x, negative e to x. In the second column, I put e3 to x, e3 to x. So that's our fundamental matrix. Now, what is it good for? Well, for instance, we can use it to express our general solution. Let's have a look at it. What happens if I take this fundamental matrix and multiply it by a vector consisting of coefficients? Well, let's see. I multiply the first row and the column, and when I do so, I get my first solution. And I multiply the second row, and I get my second solution. Or if you want, when you just use it as a matrix multiplication, you get exactly the general solution in the matrix in the vector form. So from the standpoint of abstract mathematics, this convenient matrix notation, this is very nice. This is very useful. It will come handy later on. So that would be our first fact. Nothing really deep. We just look at the formula for the solution and notice that it can be written in such a nice compact form. So that's the formula at the very end. Yx times c, where c is some constant vector. Okay. Another useful feature of the fundamental matrix is that it, in a way, serves as a Wronski matrix for the linear differential equations of higher order. How does it work? We have a system. In some way, we find candidates for the solutions. We have enough of them. For 2x2 system, we have 2 of them. And then we say, okay, is it a fundamental system? Well, we have to check on several things. First of all, we have to check that these guys are actually solutions, and that's easy. We just plug them in and see that it works. And then we have to show that they are linearly independent, and that's exactly what this matrix can do for us, just like the Wronski matrix or the Wronskian for linear differential equations. So here is the statement. We have some candidates, y1 through yn, which are solving our system on some interval. And they form a fundamental system if and only if the determinant of this fundamental matrix is not 0. Let's check. How does the determinant of our y look like? Well, I'm taking determinant, so I'm taking the product of the main diagonal, which is e2 for x, and subtracting the product of these two guys. There is another minus, so it's plus e2 for x, and I'm getting 2 e2 for x. This is definitely not 0. And this confirms that our two vectors here are linearly independent. Very nice. So, we know what to do with the fundamental system once we find it, but a good question is, how do we find it? And the answer comes in the form of a hint, because first we will just review from linear algebra. When somebody gives us a matrix, we can do all kinds of stuff with it, but one thing that we can do is to find eigenvalues and eigenvectors. So this is really just a review from linear algebra. Let's not waste time on it, and let's pass to the second statement that we have here, and that's the key statement for today. Let's see. I have a homogeneous system on the right, on the top. I find some eigenvalue with associated eigenvector. And then, when I create exponential using this eigenvalue, this sounds familiar, and I multiply it by the eigenvector, I get the solution of the given system. And if I have many eigenvalues which are distinct, then the solutions form a linearly independent set. That's very nice. Let's just briefly suggest how the proof goes. Well, let's see. I have my eigenvalue, an eigenvector. Let me call them eigenthings. Okay, this is not really formal, but okay. Now, I claim, okay, let's think back. With linear differential equations, e2 lambda naught x would be the solution. But this is just a function, and now I need vectors, vector functions. So when I multiply it by a vector, by the eigenvector, now it is a vector function. So it makes sense. And I'm claiming that this guy is a solution. How do I find out? Well, I substitute. We are using always this trick. So I substitute into the left-hand side of my equation, which I can see over here, or in the top right in my slide. I have to differentiate v e2 lambda naught x. Now again, we have to call to the theory of vector functions, how such a derivative works. This is vector, but these are constant, so they can be pulled out. That's the good news. And then we differentiate just an ordinary function, which is an exponential, our favorite derivative, probably, or perhaps the second most favorite derivative. I think differentiating 0 is also very convenient. Anyway, here we go. Now, let me make a little tiny change. I'm going to switch the order here. This is psychological, of course. Mathematically, it's the same. But now I look at it and I say, oh, wait a second. Lambda naught is eigenvalue of my matrix A. And V is actually its associated eigenvector. So lambda naught V is the same as AV. And now I look at it and I say, oh, that's wonderful. This is A, and this is actually Y. And I look at it, and I can see that that's the right-hand side of my equation, and I'm happy. Everything worked out. So that's the first statement. When you know the eigenthings, you know your solutions. That's wonderful. Now for the second part, linear independence, that's actually done by taking those, roughly speaking, taking those candidates and putting them into a matrix and playing with it. There are little details. It's a little bit longer, so let's skip it. If you're curious, it's in every good book on linear differential equations. So that's the way to actually solve systems, homogeneous systems of differential equations. Let's have a look at it. We have a nice example over here, So let's try to solve it again as if we didn't see it before. So somebody gives us a system like that. Perhaps I should copy it so that we have, we have it in one place. So somebody gave us such a beautiful 2x2 system, and they expect us to solve it. So first we recall that elimination is actually banned. Okay. So we are supposed to use the matrix approach. Let's rewrite it in the matrix form. Or perhaps we do not feel like it because we do not really need it. All we need is to know the matrix of the system. So we get it from here. It's matrix 2, 1, 1, 2. And now we can start with the matrix magic. So first of all, we need to find eigenvalues, eigenvectors. For that, we have a procedure. Okay, we are supposed to take the determinant of this matrix, but modify it. We should subtract lambda on the diagonal. So it's A minus lambda times identity matrix. And now this determinant should be 0. So let's see how much it is. This is 2 minus lambda squared, actually, minus 1. Let's multiply out. This is actually lambda squared minus 4 lambda plus 4 minus 1 is plus 3. And we are asking, could it be 0? And the answer is, of course. And the eigenvalues are 1 and 3. Now, let's think back to the previous lecture. By a remarkable coincidence, we took the system. Using elimination, we reduced it into one linear differential equation of order 2. We solved it using characteristic numbers. And those characteristic numbers were 1 and 3, with the same characteristic equation. Is it surprising? The answer is no. This system actually describes something which is happening in nature, perhaps. Some process, let's say a physical process. And this process has certain characteristics. It has certain behaviors that it prefers, and the behavior of the system is encoded by those lambdas. It doesn't matter whether we call them eigenvalues or characteristic numbers. When we take a system and reduce it equivalently into one equation, it still describes the same process. And therefore, the characteristics must be the same. Okay? So this is not really surprising. We can see the correspondence. So we have our lambdas. Now we need to find eigenvectors. Okay, let's say over here. For that, we also had a procedure. So we have to take this matrix with lambdas and put 1 for lambda, and we get 1, 1, 1, 1. We multiply it by some unknown vector, and we want this to be 0. So this matrix must be singular. Otherwise, we have made a mistake somewhere along the way. And it is singular. So I just look at the first equation. V1 plus V2 is 0. And I find some non-trivial solution. So I cannot put 0 for V1 or V2. So let's say that I put 1 for V1. And then, from the equation, V2 must be negative 1. So the eigenvector is 1, negative 1. And there will be several of them. Let me call it VA. You will see soon why. I actually prefer it that way. Anyway, I have eigenvalue, which is this guy. I have eigenvector, which is this guy. And therefore, according to our theorem, we are getting the first solution into our basis. And let me call it YA. YA is eigenvector times exponential created by the eigenvalue, which is simply vector function e to x minus e to x, which is exactly this one. Okay? It seems to work. Wonderful. It's just not very friendly, but that's life. Eigenvectors, eigenvalues, this is not too bad. You can ask computers to do it for you. Okay. The second solution. I take lambda equal to 3, I put it here in place of lambda, and I'm getting negative 1, 1, 1, negative 1. Is this matrix singular? Yes. The second row is the first row times negative 1. Yeah, it's singular. V1, V2 is supposed to be 0, 0. Actually, an experienced solver would not even bother writing the whole system. Experienced solver would just look at the first row and use it to deduce the equation. Minus V1 plus v2 is 0. Or if you want, you can use the second row. Perhaps it would be a little bit nicer. Anyway, I can choose v1 to be, let's say, 1, and then from the equation v2 is also 1. And the second eigenvector for the second eigenvalue is 1, 1. And again, I go to my friendly theorem, and it says, okay, if you want a solution, let's call it yb, then this solution will be the eigenvector times the exponential. Now lambda is 3, which is giving me the solution e to 3x, which is exactly where I was before. Yep, here we go. And then, once we have one solution, second solution, according to the theorem, my lambdas are distinct, so these are linearly independent, and we can write a general solution. General solution is just a times vector ya. Now you can see why I'm using subscripts a and b, because it allows me to be organized, plus b times yb. Or if you want, you can call them y1, y2, and then you have it exactly as in the theory. And then instead of a and b, you can use c1 and c2, and you are really in tune with the theory as we are developing it. Okay? I'm just too lazy for that. I think for the reader, not having to decipher indices is much more convenient. Okay? But that's just my personal opinion. Anyway, you work it out, and you get exactly the same solution that we had before. So this is actually a blueprint for solving systems of any size. If I give you a 5x5 system, well, you find the matrix of the system, you find eigenvalues, probably 5 of them if you get lucky. For each of them, you find eigenvector and so on. A computer can do it easily. I wouldn't do it by hand, actually, for a 5x5 systems, but I can see how it works. So this is definitely something that is nice. This is viable. Before we move on, let me talk about something. When we talked about differential equations of order 1 and also of higher order, we said that some solutions are special. They are interesting from practical point of view. And one such a type is stationary solutions, constant solutions. You can set up the system, the process which is governed by the system. You can set it up in different ways at the start. And perhaps if you set it up in a special way, it will stay that way. It will never change because it likes that setup. Stationary solutions. Are there any stationary solutions? The answer is yes. When you have a homogeneous system of equations, there is always stationary solution, namely the trivial one. If you put 0 for a and b, you get a 0 vector. If you get 0 for a and b, you get functions y1 equal to 0, y2 equals to 0. That's a stationary solution. y1 is equal to 0, y2 is equal to 0. And the question is it stable? Good question. We will talk more about stability in our special lecture on analyzing systems, and that's very useful. So let's just here go by the ear. Let's recall the basic ideas from ordinary differential equations when we had them before. Stability means that if you sort of move your system a little bit away by some outside influence, then it goes back to the stationary solution. That's what we call a stable solutions intuitively. So my question is, if I take some solution which is nearby, which is close to the constant solution, and I start letting the time go all the way to infinity, will this other solution go to my stationary? So the question is, if I look at solutions, do they go to the 0 vector? That's actually the bottom line question. Do all the nearby solutions go to 0? Because then they are actually going to this stationary solution. And the answer is, in this example, that actually probably no, when I look at it, because, well, I have a combination of vectors that look like that, or perhaps I look here at my formulas. These are quite friendly. And when I let time go to infinity, this is not going to 0, because the exponentials just blow up. Of course, a lot depends on a and b, but the trick is, if you want stability, you need all solutions to go to 0. So it's quite obvious, if you let's say, put 0 for A and 1 for B, you are just looking at exponentials. They blow up, they go to infinity, and they spoil stability. So this solution that we found here means, and it shows, that the stationary solution, the trivial solution, is unstable for this system. Okay? And this is a useful information in some applications. So it's good to be able to look at the system, look at the solution, and say, okay, the trivial solution, stationary solution, is it stable or not? And you just look at it and use common sense. We will learn more about it later on. But just on the level of intuitive reasoning, when you look at the solution and those exponentials, you should be able to tell, is the stationary solution stable or not? Okay, we'll practice it a little bit more. Okay, that was just a little side trip. Let's go back to our situation. Somebody gives us a system, we found the matrix, or well, find, that's a big word. We just tried the matrix of the system, find the eigenvalues, and if we get lucky, what does it mean getting lucky? If they are real and distinct, then we get our fundamental system. So let's ask, what happens if we are not that lucky? And for that, we will need some room. Here we have a really, really nice second-order differential equation that we can solve like on 2 lines or 3 lines at most. But we are not going to do that because it would not help us very much. Instead, we will use it to practice the tricks that we learned here. First of all, we will transform it into a system, and then we solve it using the matrix approach. Let's see. I first transformed this equation into a 1-by-1 system by attaching index 1. So y1 is my new unknown function. And now I use the reduction exactly as we practiced it. I take the derivative of y1 and I hide it by calling it y2. And then y1 derivative, the second derivative, becomes just y2 derivative. Plus 4y1 is 0. So let's write down the system. y1 derivative is y2, and y2 derivative is negative 4y1. So that was the transformation. Let's see. The matrix of the system is 0, 1, negative 4, 0. Let's hunt for eigenvalues. Determinant of negative lambda 1, negative 4, negative lambda is lambda square plus 4, and this is supposed to be 0. Lambda is, okay, plus or minus 2i. Complex eigenvalues. That's something new. We didn't have it before. Anyway, eigenvectors. When lambda is 2i, then we are actually asking for this, a matrix, where in the first row there will be negative 2i, 1, and here negative 4 and negative 2i. Is this matrix singular? That's a good question. If I take the first row and multiply it by negative 2i, then of course the second column fits, and the first column, negative 2i times negative 2i, gives me negative 4. Yeah, it fits. The second row is a multiple of the first row. Good. So far, things work out the way they are supposed to. I put together an equation, and let's say that I pull from the first row. Negative 2i v1 plus v2 is 0. If I choose v1 to be 1, which is quite popular actually, then this will be negative 2i. I move it to the other side. v2 is 2i. So the eigenvector is 1, 2i. I look at it, I have an eigenvector, I have eigenvalue. I say, well, there should be a solution, which is my eigenvector, 1, 2i, multiplied by exponential based on my lambda, 2ix. That should be the solution. Is it a solution? Yes, it is a solution. Because the theorem that we have here is general. It also works for complex lambdas. Do I like this solution? And the answer is no. I prefer to have real-valued solutions to my real-valued problems. So what do? Well, let's think back. Some time ago, when we looked at linear differential equations of order n, we had the situation that lambda could be complex. And then, of course, you get the complex solution e to alpha x plus beta I x. And we said, okay, no problem. The real part is just an exponential, and the complex part, it actually encodes sines and cosines. So we split it into two solutions. One of them had cosine with frequency beta, and the other one had sine with frequency beta. Will the same work here? The answer is no, unfortunately. So this is a really good thing for linear differential equations, but I recommend it when I was actually telling you about this, that one should also remember how this comes. Where do these two formulas come from? And the answer is they come from this formula using real part and imaginary part. And this idea works also for systems. So what we should do, we should find the real part of this and the imaginary part of this. Which is not easy. And you can notice that if we had just the exponential, then, yeah, finding real imaginary part would just introduce cosine and sine. That would be nice. But when you have a complex eigenvalue, you can also expect to have complex eigenvector. So real complex parts from the vector interfere with real complex parts of the exponential. And we have to figure out what is the outcome of this influence. So first of all, I'm going to write it as 1 to I times. And now I would put the real part, if there was any real part, e to alpha x. But here the real part is 0, so I'm not pulling it out. And then I look at the imaginary part, and I write it using the trig formula. So it's cosine to x plus I sine to x. And now I'm going to multiply vector and this formula and see what happens. So it's cosine to x plus I sine to x. And in the denominator, I'm actually multiplying this addition, this combination, by 2i. And I prefer to have the real part in front. So 2i multiplies i's, or I, and becomes just -2. So this will be the real part. -2 sine 2x. Then 2i multiplies cosine, and that would be the new imaginary part. Actually, rounded bracket, like that. So my solution actually looks like this. And now from this solution, I'm going to identify the real and imaginary part. So let me split it again. This is cosine 2x, -2 sine 2x, plus I times sine 2x, 2 cosine 2x. Okay. Now I take real part, I take imaginary part, and I prepared it in such a way that I can see it right away. Real, imaginary. So my solutions look like that. The first solution, and again let me call it YA, is the real part of Y, which is cosine 2x, -2 sine 2x. And my second solution is imaginary part of y, which is sine 2x, 2 cosine 2x. I've got YA, I've got YB. I have a 2-by-2 system, so I have enough functions for my fundamental system, and I can write the general solution. General solution in the vector form is A times cosine 2x, negative 2 sine 2x, plus b times sine 2x, 2 cosines 2x. Okay, that's the vector form, but for the user, let's be nice. Let's write it as y1 x is equal to y2x is equal to. So I multiply out a inside, I multiply b inside, I merge them, and in the first row I can see y1. y1 is a cosine 2x plus b sine 2x. y2 is negative 2a sine 2x plus 2b cosine 2x. X belonging to real numbers, probably. Is there any trouble in my system? No. Is there any trouble along the way? In the answer, no. X belonging to R. And we are done. And going back to my original question, now I discard y2, I just take y1, and that's the solution of the original equation. Hooray, we are done. Okay, several remarks. First of all, does this work? Is this trick general, or were we just lucky? The answer is yeah, that's exactly the way this is supposed to work. Here we go, confirmation. So if you have an eigenvalue which is complex with non-zero imaginary part, then you take your solution, which is the eigenvector times the exponential, and you take the real part, you take the imaginary part, and they are linearly independent. Wonderful. So this is actually the procedure for handling complex eigenvalues. Now, why don't I worry about negative 2i? The answer is exactly the same as it was before for linear differential equations. If I play with negative 2i, I get the same basis. Only one of those vectors will be opposite, will have minuses. But that will be the only difference. So it is still the same space, still the same two-dimensional space. I would just get a slightly different basis, which is useless because I have the basis anyway from lambda equal to 2i. So this is wonderful. You just choose one of them, work them out. Let's go back to this idea of a stationary solution. I have a 2-by-2 system which is homogeneous. So one of the solutions is the trivial solution. Let me add a variable here so that it's really emphasized that this is a function which is identically zero, a constant solution, stationary solution. This is a stationary solution of our system. Is it stable or not? So let's have a look at our formulas. When I send x to infinity, will I see y1 and y2 going to 0? And the answer is, of course not. These are oscillating functions. So this is again unstable because y1 doesn't go to 0, which is enough to prevent stability. And of course y2 doesn't go to 0 as well. This only confirms that things are unstable, which in some applications may be very unpleasant. Which brings me to the second remark. This is an equation which is from applications. And when I introduced this idea of transforming equations into systems, I said it's beneficial. But now here we have an equation which can be solved directly on like 3 lines, and we followed an alternative way through systems which is, let's say, somewhat longer than 3 lines. So there must be some really massive benefits, shouldn't they? Well, actually, not quite. See, the benefits mainly come when the equation is less friendly. For instance, a minor modification, which does appear in applications, changes this equation into something which cannot be solved analytically, and then the transformation into a system is beneficial, definitely, but we do not just see it here. Let me show you one minor benefit. When this equation appears in applications, then y1 or y typically describes position, and then the derivative is velocity. So when you are solving it as a system, you get immediately, for free, information about both position and velocity. So this is sometimes useful. Okay, so that's a minor benefit that we can see here. Just out of curiosity, this is a very special system because it comes from reduction. So we can also expect the solution to be special. How special? Well, y2 should be derivative of y1. Is it true? y2 is derivative of y1. Yeah, it checks out. So things fit together. But in general, if I just give you some system, any system, of course this no longer works. But the procedure as we outlined it is valid. Okay? So that's the procedure for complex eigenvalues. Let's see. We know how to solve eigenvalues that are distinct. We know how to work out complex eigenvalues. What happens if we have eigenvalues which are the same? In other words, eigenvalues of higher multiplicity. For that, we also need some room and a new slide. Here we are, ready to tackle the last remaining important case. We have a homogeneous system, we found eigenvalues, and one of them actually has higher multiplicity. We need to know what to do with that. So first, we borrow something from linear algebra. When we have eigenvalue of multiplicity m, then there are m so-called generalized eigenvectors. And we find them exactly the way they teach us in linear algebra. And after we find these generalized eigenvectors, we use them to form our solutions. And as you can see from the formulas, this is not exactly friendly. There are some really interesting things happening. This is definitely not so easy like we had it for linear equations, linear differential equations, where we simply used exponential and then x times exponential, x squared times exponential. That was simple. This is, let's say, slightly more challenging, but not difficult, just long and boring. Let's see. Here I have a 2x2 system, and just for the sake of completeness, I also added initial conditions so that we can review initial value problems at the end. Okay. Let's work it out. 2x2 system, I change it into matrix form, which I'm too lazy to write down. I just mark the matrix of the system, which is -1, 1, -1, -3. That's a lot of negative numbers. Anyway, let's find eigenvalues. I add a negative lambda or subtracted lambda on the diagonal, and I work it out. So what's the determinant? Okay, I'm multiplying these two guys, and let me write it down. -1 minus lambda, -3 minus lambda, and then there is +1. And I don't really like it very much, so I'm going to pull out minus from the first bracket, minus from the second group. 2 minuses give me plus. That looks good. Lambda +1, lambda +3, +1. Is it necessary? No. Is it helpful? Yes, because mathematics is to a large extent psychological. If you like the formula better, you are less likely to make a mistake. So let's see. Lambda squared +4 lambda +4. Of course, assuming that you do not make an error when rewriting formulas so that they look better. Anyway, let's go back to my problem. I remember this from childhood. I've been using this formula a lot. This is lambda +2 squared. And I'm asking, is that 0 sometimes? And the answer is definitely yes, when lambda is -2. We have our eigenvalue, and it's eigenvalue of multiplicity 2, or double eigenvalue if you want. Okay, here we go. Lambda is -2. How about the eigenvectors? Well. Here is the matrix. I put -2 for lambda. I get 1, 1, -1, -1. Again, the matrix is singular. So far, so good. V1, V2 is equal to 0, 0. So let's say from the first row, V1 plus V2 is 0. I choose V1 to be 1. That's my personal choice. And then V2 will be -1. And what do I see? I see eigenvector V, which is 1, -1. And therefore, I have my first solution, YA, which is 1, -1, times the exponential, e2 -2x. Do I feel like rewriting it? And the answer is, okay, I do. So it's e2 -2x minus e2 -2x. Nice. That's my first solution for my fundamental system. Where do I find the second one? I need to find generalized eigenvector. How do I find it? Let's see. Do I see it over here? No. Let's go back. Here is the advice. After I find V1, this is actually V1, I should solve a system of equations, which is exactly this system, but instead of 0 on the right, I should put V1. So it's like a chain. You keep recycling the matrix of the system. You keep recycling your unknown, essentially. But here, you always put the latest information that you have. 1, -1. That was my latest information. OK. Again, this is a system which is no longer homogeneous. So let's imagine how the extended matrix looks like. I would take this column and attach it here, 1, 1, 1, -1, -1, -1. That's a singular matrix again. OK. Let's see from the first row. V1 plus V2 is 1. The fact that the system is not homogeneous allows me to do something which I couldn't do before. Notice this is a homogeneous system and I need a non-trivial solution, so I needed to choose V1 different from 0. But now I can actually afford to choose V1 0 and V2 becomes 1. So the vector as such is non-trivial. This is allowed. OK, let's see. Vector V2 is 0, 1. And if my lambda had multiplicity 3, then I would again set up a system, and this vector would become the right-hand side, and so on. Keep going like that. Anyway, this is not a review of linear algebra. Let's move on. I have V2, and therefore I have vector YB, which is, now let's be careful. I have to take the previous vector and integrate it, which means I multiply it by x. So this vector gets multiplied by x, and I add the new vector. And this is a vector which multiplies my exponential. Am I right? Let's see. That's the second, well, the second last row over here. I can see it here. Yeah, that's exactly the formula. V1x plus V2. OK, do I feel like rewriting it? Perhaps yes, here. So in the top row, I can see x and the exponential. And down here, I can see minus x plus 1. How do I write it so that it's nice? Probably like that. Minus x plus 1 multiplied by the exponential. Why not? OK. Let's move on. I have two vectors for my basis. Here they are. And therefore, I can write a general solution. But I'm not writing the worst general solution yet, because this is preliminary. A times the first vector, e to negative 2x, negative e to negative 2x, plus b times the second guy, x e to negative 2x, minus x plus 1, e to negative 2x. Why is it preliminary? Because I'm nice on people, on my customers. Now I am telling them that the general solution is y1x is equal to, and y2x is equal to. And let's trace it. The first row, a times the exponential, e to negative 2x, plus bx e to negative 2x. By the way, when solving linear differential equations with lambda of higher order, this is exactly what we do. We set up the exponential, then we take x times the exponential, then we take x squared times the exponential. It's nice. But unfortunately for systems, it doesn't quite work, as we will just see. Minus a e to negative 2x plus b times minus x plus 1 e to negative 2x. Any restrictions anywhere? Not really, not really. Everything is fine. So region of validity, x belonging to real numbers. And that's the general solution. So it wasn't so bad after all. It's just long. So I'm not going to ask for something like that on a test. Not that it's difficult, but it's long. And in fact, it doesn't appear in application a lot. So if you encounter it, which will most likely never happen, but if you do encounter it, you will look it up in my lecture notes or in some textbook. Yeah, you will just follow the advice, essentially. Okay, there is one last remaining case. What if you have a complex eigenvalue of higher multiplicity? And the answer is, then also the eigenvectors will be complex. So you work out your solutions exactly using this pattern, and then you split each of them to real imaginary part, real imaginary part. Whoa, we are not going to even do an example for that, because this really almost never happens. But we know how to handle it. That's important. We know how to deal with it. Okay, let's see. We've got general solution and initial conditions. One more thing to do. So all this was actually stage 1. Stage 2, initial conditions. Well, let's see. y1, y2 is over here. I'm supposed to substitute 0 for x, and there are some prescribed values. So I substitute 0 for x, and I get a. And I substitute 0 for x, and that's it. A is equal to 13. Now, that's an equation that I like. Okay, here we go. Substitute 0 here, negative a. Substitute 0 here, and I get plus b is equal to 23. I think so. Actually, that's one of my favorite numbers too. 2 by 2 system, let's solve it. A is 13. Now, I put 13 here for A, and B happens to be 13, move here, 36. So, let's write down the solution. And this is the solution of the given initial value problem. A is 13, and also for y2, it's negative 13. Exponentials, e to negative 2x. Then there is plus b, and b is 36, plus 36, plus 36. On the top, the first function x e to negative 2x. The second function minus x plus 1 e to negative 2x. And that could be it, but now that I am looking at it, perhaps I would like to break this one into 2 parts, because I can see some exponentials and I can see some exponentials here. So perhaps I can put them together. Will it be nicer? I don't know. Let's play a little bit. So here negative 13, here plus 36. So that gives me 23 e to negative 2x minus 36 x e to negative 2x. X belonging to real numbers. Does it look better? I am not sure. Was it worth it? I don't know. Anyway, we've got it. So that's the particular solution corresponding to our given initial conditions. This was just a review. Easy. This we know really well. So that's it for this problem. One more case remaining. What if somebody gives you a complex eigenvalue with higher multiplicity? What do you do then? Well, you follow this path. But then the lambda will be complex. Also the eigenvectors, v1, v2 will be complex. So the solutions will be complex, and you take the real part, the imaginary part. Real part, imaginary part, and we get our fundamental system. Did I write a slide for that? No, I didn't. Do I feel like showing an example? Not really. You will never encounter this example. But the important thing is, it's written in some books, you can find it, and we know how to deal with it. That's the important part. So we actually know how to deal with any kind of eigenvalues. In other words, any homogeneous system of linear differential equations we can handle, assuming that we can find eigenvalues. Now that's a good question. And not surprisingly, there will be a lecture on finding eigenvalues of matrices, especially if they are large. So this much for this example, but a little bonus. We found a general solution. And our system happens to be homogeneous. Because it's a homogeneous system, it does have a trivial solution. Yx is identically equal to 0 for any x. And this trivial solution happens to be a stationary solution for our system. Is it stable? That's a good question. we will have a theory for that, but again, intuitively, a stable solution is a solution which is stationary, and all other solutions which are near go to it. So here we have all our solution. What happens to them when x goes to infinity? Well, this exponential goes to 0. This exponential goes to 0. That's nice. How about this guy? Exponential goes to 0. X goes to infinity. Indeterminate expression, but this is actually x divided by e to 2x. And we know from calculus that when we ask about what's happening at infinity, then the exponential is dominant. It beats the power, and the answer is 0. So this term goes to 0 for the same reason. This term goes to 0. All the terms go to 0. So in fact, y1 goes to 0, and y2 goes to 0 as x goes to infinity, regardless of your choice of a and b. So all solutions of our homogeneous system, they go to the trivial solution, and therefore this guy is stable, which in applications can be a very welcome information. And that's it. That's it for the homogeneous systems. We know how to handle them. And now the next question is, where do we find that elusive particle solution? And that's exactly the topic of the next lecture. See you there. Negative 2i, 1, and here negative 4 and 2i. Is this matrix singular? That's a good question. If I take the first row and multiply it by 2i, then of course the second column fits, and the first column, negative 2i times 2i, gives me negative 4. Yeah, it fits. The second row is a multiple of the first row. Good. So far, things work out the way they are supposed to. Negative 2i, 1, and here negative 4 and negative 2i. Is this matrix singular? That's a good question. If I take the first row and multiply it by negative 2i, then of course the second column fits, and the first column, negative 2i times negative 2i, gives me negative 4. Yeah, it fits. The second row is a multiple of the first row. Good. So far, things work out the way they are supposed to. But in general, if I just give you some system, any system, of course this no longer works. But the procedure as we outlined it is valid, okay? So that's the procedure for complex eigenvalues.